I am continuing to record podcasts despite the banging going on in the apartment below because that's not going to stop for some time. And I don't want to be idle for so I can do this in the office, but you have other problems there, people coming and going. But nonetheless, there are many papers on the impacts of El Nino on a monsoon, and clearly we still don't have a complete understanding. This is one of the more recent papers, so I'm going to take this just to jump ahead in terms of how the analyses have evolved. This talks about regional and temporal variability of Indian summer monsoon rainfall in relation to El Nino southern oscillation. The most important thing to remember always is that El Nino is evolving during the summer monsoon season, peaks in December, January, February, leaves a signature in ocean temperatures in the following spring as well. So there is some evidence that El Nino affects the following year's monsoon as well through the Indian Ocean warming, for example. Okay, the Indian summer monsoon rainfall exhibits significant variability affecting the food and water security of the densely populated Indian subcontinent. The introductory statements we have to all use. Lot of noise. The two dominant spatial modes of ISMR Indian summer monsoon rainfall variability are associated with the El Nino southern oscillation and the strength of the semi-permanent monsoon trough, along with the related variability in monsoon depressions, respectively. So you have synoptic scale monsoon depressions. There are 3 to 10 days and 10 to 20 days, 20 to 60 days. All kinds of time scales are there. Although the robust teleconnection between ENSO and ISMR have been established well for several decades, the major drivers leading to the time-varying relationship between ENSO and ISMR patterns across different regions of the country are not well understood. So obviously they are going to do that in this paper. Our analysis shows a consistent increase from a moderate to substantially strong teleconnection strength between ENSO and ISMR from 1901 to 1940. So we are looking at decadal regimes of strong and weak correlation between the two. This strengthened relationship remained stable and strong between 1941 and 1980. However, in the recent period from 1981 to 2018, the teleconnection decreased consistently again to a moderate strength. We find that the ENSO-ISMR relationship exhibits distinct regional variability with time-varying relationship over the North, Central, and South India. Specifically, the teleconnection displays an increasing relationship for North India, a decreasing relationship for Central India, and a consistent relationship for South India. So we are talking about longer than a century in terms of the analysis period over which extensive global warming has happened, and yet we are talking about the relation between ENSO and ISMR. So you have to remember that how global warming changes the monsoon, the ENSO, and their relation is not completely captured in these kind of analysis. Warm SST anomalies over the where are they? Warm SST anomalies over the eastern Pacific Ocean correspond to an overall decrease in ISMR, El Nino response, while warm SST anomalies over the Indian Ocean corresponds to a decrease in rainfall over the north and increase over the south of India. Okay, so that's the Indian Ocean warming. The central Indian region experienced the most substantial variation in the ENSO-ISMR relationship. This variation corresponds to the variability of the monsoon trough and depressions, strongly influenced by the Pacific Decadal Oscillation and the North Atlantic Oscillation, which regulate the relative dominance of the two spatial modes of ISMR. So you take the ISMR, you make spatial EOFs on spatial loading and time series associated with it. And remember that you have the onset of the monsoon, a season, a active break periods, the withdrawal, and you have the trough movement. They can all be affected by not just El Nino, but also uh, North Atlantic oscillation, Pacific decadal oscillation, now even the Arctic sea ice loss, Southern Ocean is also affecting the Indian monsoon and so on. But uh, we apply the principal component analysis biplot technique. Our study highlights with this that the significant impacts of various climate drivers on the two dominant spatial modes of ISMR, which account for the evolving nature of the ENSO-ISMR relationship. Just kind of putting it all together over time. So we'll just look at this figure. We are looking at EOF1, kind of a subcontinental scale monopole, and EOF2, this explains 15.11% of the total variance, and this explains 8.48%. So it's not a huge, usually the principal component can be as high as 50%. If you do SST anomaly PCA, El Nino gets maybe 50% or more. Whereas here you are getting small numbers, but this has a kind of a dipole north-south mode, and this is also related to the ocean because there is a connection this way, and sometimes you see a connection this way, so you can think of this and this as a dipole as well, and this and this, and so well, this is PC1 is obviously highly correlated to Nino 3.4, so highly means it's 0.54, so only about 25% of the explained variance, which means you are really talking about low signals. PC2 time series is correlated with the combined ISMR PC2, and looking at vorticity at 850 hectopascal, low correlation but statistically significant at 0.362, and this is the depression frequency time series, again correlation at only 0.276, but they are invoked for explaining this relation here, spatial bipole kind of relation. Here correlation map between SST and PC1, basically El Nino pattern evolves, but you can see there is also the IOD type, at least this part of the IOD here. Between PC2 and SST, you get some signature here in the North Indian Ocean, some part here, and the South China Sea, and obviously also with vorticity and depressions, low pressure system frequencies. This is omega, the vertical velocity in pressure coordinates at 500 hectopascal, which tells you about the heating and the vertical motion. Winds shear 700 to 1000 HPA mean, and PC1, all kinds of complicated patterns. I'm not going to go into it, but essentially you have two dominant patterns. One has a dipole-like structure. Remember, these are not positive negative because it depends on the time series. So if the time series is negative, then this will multiply it and become negative. This is a negative, then this is positive. Blue is negative. So when there is an El Nino, there is reduced rainfall, and here you get not so much correlation with Nino 3, but other ISMR and PC2, etc. Okay, basically there are complicated relations, and if you extend it, then you will find PC2 and PC1 also have various correlations with what they call PCA biplot approach for 1901 to 2018. You are not assuming, you are not including any regime change. You are considering the whole period, because you can always do this based on regimes where the relations are weak or strong. So you get different answers, but nonetheless, here is the inter-hemispheric Pacific oscillation, quasi-biennial oscillation. I hope it's quasi-biennial. North Atlantic oscillation, and MDF is the monsoon depression frequency, monsoon trough, and so on. And so Pacific decadal oscillation here, Indian Ocean basin mode here, and IPC2 is the PCA biplot of different climate mode indices. So PC1 with ISMR is called IPC1, and PC2 with ISMR is called IPC2. What does it get you? Basically, it says that there are many players in impacting the monsoon, and who dominates when may depend on various things. But El Nino is dominating PC1, but El Nino and monsoon correlations are not stationary, as we will see. So why do they vary in time? Maybe some other players get more dominant. Okay, there is something called ENSO variability as well, because ENSOs themselves are not occurring with the same number or intensity in different decades. So you can think of El Nino itself having a variability at low frequencies. Okay, this figure here is showing composites of seasonal June, July, August, September rainfall, SST, and 500 hectopascal geopotential height anomalies for PC1 greater than its positive standard deviation, PC1 less than its negative standard deviation. So you look for excess years, deficit years, PC2 greater than its positive standard deviation, PC2 less than its negative standard deviation. Basically, you are talking about uh, deficit years with ENSO impact, the excess years with La Nina impacts, and the PC2 with the forcing that is more like a interhemispheric Pacific oscillation kind of impact with some signatures in the Indian Ocean, and of course there are other signatures as well. Okay, so PC2, PC1, what else can I say for it? This is PC1, PC2 with +1 standard deviation, PC2 minus standard deviation. So you can see out of phase, green, purple, uh, green, purple. So you flip obviously. So you get the idea that there are all kinds of influences and it's not always easy to say what is causing what at any given time. Nonetheless, there are regimes. So you're looking at 1901 to 1940 regime, 1941 to 1980, 1981 to 2018, and the correlations between ISMR and Nino 3 are varying. So Nino impact is strong, negative in some decades, weak, weak, stronger, remains strong and weakens again. So do we explain all these things exactly how they happen? When you have so many players, then you don't know the cause and effect, because correlations never tell you cause and effect completely, right? So you can also look at spatial map of correlation between ISMR and ENSO for the whole period 1901 to 2018. 30-year running mean correlations between ISMR and 3.4. Spatial map of correlation during 1901 to 40. 1901 to 1940, 41 to 80, 81 to 2018. So again, the main point is that the PC2 kind of relation, South India doesn't seem to vary much over the whole period, whereas North India has a stronger correlation, as does Central India. That's what we tried to capture with PC1 and PC2. Am I being very clear? Not necessarily, because the entire business is about finding correlations and not always fully explaining. El Nino and monsoon correlations are the easiest to explain in terms of the perturbations to the Walker cell and hence the local Hadley cell over the monsoon. But we also talked about how transitions from winter La Nina to summer El Nino, or winter El Nino to summer La Nina have sometimes bigger impacts, because there is a whiplash effect. If you are in a La Nina winter, the Walker cell is stronger and the warm pool is pushed to the west warmer, and then if transitions to El Nino like it's doing in 25 winter state to 26 summer state, then there is a quick departure to the other side, with warm pool becoming weaker, cooler, and spreading to the east, Walker cell shifting and impact on the monsoon is the strongest during such a transition. Okay, let's leave it here, but basically you have to go and read these papers, because all I'm doing is raising questions about what do we really understand, because beyond the fact that El Nino impacts the monsoon, generally giving us deficit, but only 60 or so percent monsoon deficits are related to El Ninos, 60 or so percent excess years are related to La Nina. So monsoon has a lot of internal variability or impacts from all these other alphabet soup of climate modes. Okay, let me leave it there.